there. All right, first box was what? Mixture of elements or diatomic?
Diatomic.
So diatomic elements. Here we go. So you need to have a few molecules that are maybe two white ones touching, and then a few molecules with two black ones, or whatever color your pen is, obviously. So two that are not shaded touching, and then two that are shaded touching, right? That's a mixture of diatomic. Okay, again, it could be hydrogen gas and oxygen gas. Okay, what was this one? I keep forgetting.
Compounds.
Mixture of compounds. So just like we did for the warm-up here. If you do maybe 3 of these, right? So there's one type of compound, shaded with an unshaded, and then maybe water. Okay, so the Mickey Mouse, and mix them up a little bit, and there we go. So that would be a mixture of compounds. If you have a different type of compound, that's fine, as long as it's 2 different colors. Okay, so that's one type of compound, water is another.
Water vapor plus iron.
Water vapor, so we got to put water vapor kind of spread out throughout the box, right? So maybe I'll put 3 of them there. So there's water vapor, and then iron, you said? Iron is monatomic, right? And I'm careful, I don't want them touching, right? Because then you might mistake them for diatomic. And now some kids might argue with me, wait. If this is oxygen, right? Water is H2O, so if hydrogen is this, and oxygen is that, which looks weird, but then iron, we would have to give a different symbol. All right, you could just put a line through it or an X through it. If that makes you feel good, then do it. If not, I don't really care too much about it. I just wanted you to show water vapor, what that looks like, and then a monatomic solid. So technically it should be a different symbol, because if we left it like this, it looks like it's oxygen, right? Don't worry, on a Regents or a test, the key will be provided, so they'll tell you what to use.
It's carbon dioxide at STP.
Carbon dioxide at STP. So at STP, so at 0 degrees Celsius, the reason I told you that is just because you're going to see it on a test or a Regent. CO2 in this room is a gas. At STP, it's still a gas. It has to be like negative, I don't know, 100 or something for it to be a liquid. So CO2 looks like this. We'll do carbon here, and then the oxygens are white. If you flipped it, that's fine. All right, so just make sure you always draw at least 5 or 6 particles, right? So CO2, so carbon would be the black one here, the shaded, and then oxygen would be unshaded. CO2 would fill the box, it's a gas. Questions? We only spent a couple days on this, or a day and a half, and I'm already tired of it. So hopefully you are too, and hopefully it's easy. Okay, the only other thing I do want to mention is, yes, almost all of these are molecules, okay? But just make sure you know these are molecules but elements. These are molecules but compounds. Molecules, compound. Atoms, elements. You can't have a compound that's an atom. It's impossible. You need at least 2 atoms to be a compound. So these are atoms, also an element, molecules, compound. So just be able to, by Friday, understand what solids look like, gases look like, liquids look like, what atoms look like, what molecules look like, what elements look like, and what compounds look like. That's everything. Okay. Now, before we hit the lights, next part of our notes. Oh, that's unfortunate. As it gets colder out, it gets annoying in this room because this wall goes right outside. The board gets absurdly cold, so it doesn't erase very well. So there's going to be like shadows, which makes me crazy, but it is what it is. All right. Okay, here we go. Let's talk about the kinetic molecular theory. Kinetic molecular theory. And I wanted to show you a demo today, but if we don't get to it, I will show you tomorrow. We're going to talk about gases this week. Kinetic molecular theory applies to all solid, liquids, gases, but gases it's a lot easier to focus on. I'm going to show you a video, and there's 3 or 4 main ideas about this. See what you get out of the video, okay? So you're going to watch the video. It's on the kinetic molecular theory, and let's write down what we learn in the video. All right, lights please. So I won't explain any of it. You just watch this first. All right. Okay. Kira, that might be like ridiculously loud at first. I apologize if it is. I'll turn it down. Hey, do you mind getting the blinds? Just the first two. Fella, can you help actually? Thanks. Alright, short video. It's only a minute and a half. I think it's like bagpipes or something, so just get ready. Here we go. Okay, so kinetic molecular theory. It's going to be an animation. Try and get a couple things from the video. What is kinetic molecular theory? What's it all about? Here we go.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
Okay, watch again. I want you to write 3 things down that you get from this video about the kinetic molecular theory. 3 things. 3 things that you get from the video. Okay, here we go. I think I skipped this weird part here. Okay, here we go. 3 things.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
Okay. I'm going to show you one more thing here. You already saw this. I'm just going to play it again. Okay, this is another example of the kinetic molecular theory. So you wrote 3 things down. This video is focusing on gases, right? How gas particles move. So we got about 10 minutes left. By the end of class here, we're going to list, there's 4 parts to the kinetic molecular theory, and mostly how do they apply to gases. I'm going to give you a worksheet for homework, and then that'll be it for today. This week, I'm going to show you some demos with gases to help you understand concepts. Okay? There's not a lot of time today, but I want to introduce it today, and then we'll kind of learn more as the week goes on. All right. So that's how gas particles move. We've talked about that. All right. So, likes, please. Kinetic molecular theory. What's the first thing everybody heard about it? Raise your hand. What'd she say? First thing. Kiki. Right. All matter is made up of particles that are constantly moving. We already learned this. You know this. What do solid particles do? What do they do?
Vibrate.
Vibrate. Liquid particles. She said. Flow. Gas particles. Move fast. Move quickly all around. Okay? Good. Okay, that's one thing. What's another thing? We got 3 things, right? I got my list here. Anybody got something else? What do you got?
High temp and low temp equal high energy and low energy.
Okay, good. So, if particles are at higher temperature, they have higher energy. If they're at lower temperature, they have lower energy. We all agree? Don't write that yet on this list, though. Okay, that's right, but that's good. But that's something we're going to talk about later. Okay, but that's good. What's the definition of temperature? Go ahead, look in your notes. Melissa, go ahead when you find it. Definition of temperature.
Measure of the average kinetic energies of particles.
Measure of the average kinetic energy of particles. What's kinetic energy due to, Ben?
I'm sorry, what?
What's kinetic energy due to?
What does it do to?
Yep. Why does it exist? What is kinetic energy? How about that?
The measure of the energy required to move.
Good. Yes, particles moving create kinetic energy. Stored energy, like in this banana I've talked about, is potential energy. Not particles aren't really moving a whole lot. Okay, the faster they move, the more kinetic energy they have, the higher the temp. So I'm just repeating what Jake said. What else? What else did she say? That was good, Jake. So we got 2 things. The definition, that's like what it is. He said the higher the temp, the more energy. Lower the temp, less energy. What else? No one got a third thing? I think I read once or heard somewhere that you have to hear something like 7 times before you remember it. So that means I should show you every demo and every animation and video 7 times.
Sounds like the solid point.
Ain't nobody got time for that. Come on, give me another one. What else did you hear? Anything? Does anyone remember what she said about how particles move? In that video, how were they moving? What were they anyways? The little particles that were squeaking and making noises.
Water.
Yeah, it's water. How did they look like they were moving? Like they had a set path in mind? No, give me a word. Random. Who said? Randomly, right. So we're gonna write that down. This is a little star here. Number 2, this is mostly for gases, liquids too a little bit, but put in parentheses here, gases. Particles move in random straight lines. Random straight lines. The analogy I use is basketball. It's a pretty easy analogy here. Okay? If I drop this on the ground, it bounces straight up, straight back from where it came from, or at a certain angle. Okay? If I was to pass this on the ground to somebody, okay, if it hits the ground at an angle, it's going to bounce off at the same exact angle in a straight line. If I throw this off the wall, it's going to come back to me in a straight line. Okay? So when balls collide with things, they don't just, so in other words, if I was to drop this and then when it came back up, it just started doing this in the air. That doesn't make any sense, right? Particles are like little basketballs. Okay? When they hit something, they bounce off in a straight line. And you can argue, you can put spin and curve balls and base. You can argue with me, but the point is when little tiny particles collide or when they're moving, they're always moving randomly and in straight lines. They don't have brains. They're not like, oh, I'm going to go over here. I'm going to go over here. They're moving randomly, and when they bounce off of things, it's in straight lines, just like a ball would off of a wall or the floor. Okay, that's really important to remember. We'll talk more about that. Okay, what else? I guess that's our 3. That was our 3 things here. The energy she talked about, random straight lines. She said random. She didn't say straight lines. I said straight lines. And then the definition of it. I'm going to give you the other 2 so we can write down what Jake said. All right. When particles collide, so again, mostly gases, when particles collide, they change their path. Seems very obvious, but if you have two particles that collide, they don't keep going in the same direction. They bounce off and their path changes. That's kind of like, why do we need to write it? But if I was to throw that ball off a wall, it's not going through the wall, it's going to bounce and change the path, right? So when particles collide, they change their path. And now, number 4 is also very important. I need 2 volunteers. 2 volunteers. Jake and who else? Perfect. Can you guys come over to the side here or up here, whatever? You're gonna get a little physical with each other.
That's great.
Just be nice to each other, okay?
Don't kill me.
Okay. All right. Now, can you guys back up a little bit? There you go. Hold on, Ben. You go this way. Jake, go that way. Increase the distance between you. Good enough. Okay. Now, if you were to walk towards each other and then collide with each other, let's go shoulder to shoulder. Guys, what's wrong, guys? Testosterone. I just wanted you to just nudge each other, not whatever that is.
I didn't
All right,
know.
so, okay. Now, did you feel him hitting you?
Yeah.
Did you feel him? Okay. What am I trying to show? What if you ran into each other? What if they don't do it? What if they ran into each other? Would the collision be the same? Or more violent? More violent, because it'd be more what?
Energy.
More energy, more speed, right? Okay. All right, now get near each other again, please. Now do me a favor, Ben. Yeah, you need your hands. Jake, brace yourself. Push, Jake. Not too hard.
Oh,
Okay, good. Why does Jake move when he pushes him? You guys can sit down, thank you.
oh,
That's it, I just need a visual.
for that.
Why did Jake move? I mean, I could throw the ball as an analogy. If I take this ball and I throw it, it moves. Why?
You put energy in the ball.
So, what am I trying to show you? When 2 particles collide, what do they do with their energy? When Ben pushed Jake, what did Ben give to Jake? Very good. Say it louder. Transfer energy. When 2 particles collide, they transfer energy. Very good. Just like if I had Ben and Jake running at each other full steam. Something bad would happen. Okay, they'd probably get hurt. That's because they're transferring energy. When 2 cars crash, all right, in an accident, all right, let's just think of one that is very minor, right, because that can be scary. The cars usually get all smashed up. Why? They're transferring energy. If there was no energy being transferred, nothing would happen, okay? They just bounce off each other, okay? There is a transfer of energy. Every time particles collide with each other, they transfer energy. If they're moving faster, they transfer more energy. If they're moving slower, they transfer less energy. Okay? There's one more point I want to make to that, but I'm out of time. Your homework is this worksheet. All you need is this list. We didn't write down what Jake said, but that was good, Jake. You need this list, and then some of this is from stuff from last week about temperature. All right? So this is due tomorrow. This is not on your test Friday. None of this stuff we talked about today. All right? But some of the temperature questions are on the test. So Kelvin, Celsius stuff. All right? So this is due tomorrow. Feel free to put the answers on the back. Don't waste another piece of paper. Okay? Put the answers on the back for 1 through 8. 1, 2, 3 on the bottom is multiple choice. You can just circle your answer, obviously. Okay? All right, and that's it. I will be after school if you want to review for that test on Friday. And I'll give you that review sheet tomorrow. And that's it.